Hello everyone. So let's continue our analysis of three-phase circuits, and in this video I am considering star and delta circuit. That means the source is star connected and the load is delta connected. So we had seen in the earlier video source and load both are star connected. So in this we are doing that. So what is there on the source? A three-phase source of phase voltages 100, 120 and 240 with minus signs, and this is a regular three-phase voltage source, and each phase has a of the load has an impedance of 2 plus j7 ohms. So find all phase and line voltages and currents. So let's do that. Now the source is star connected, so already I have from the previous video I already have this. So you look at VA, the A phase voltage, and VB is the B phase voltage, VC is the C phase voltage, and this is the point, neutral point. All negative terminals are connected in one place, and then the positive terminals are taken out as lines A, B and C. And the line voltages VAB, VBC, VCA are defined as like this. So VAB is voltage of A with reference to B. So that's why this is plus and minus and so on. And we had seen how these things are so calculated. So for example, VA, VB, VC. So these are phase voltages, and those values are already given in the question, that is 100 0 degrees, 100 minus 120 degrees, and this is 100 minus 240 degrees. This is in volts. Now what you do, you multiply it with root 3 and angle 30 degrees. That means I'm increasing the magnitude by a factor of root 3, and then I'm shifting the angle by plus 30 degrees. Then I'll get the line voltages VAB, VBC and VCA. So these are line voltages. So these are phase voltages of source, and these are line voltages. So here we don't specify source or load, because basically they are voltages measured on the line which is connecting the source and the load. What are the values? So just see here, 100 into root 3 is 1.732. So into 100 is 173.2. I'll approximate it to 173. And the angle will increase by 30 degrees. So this we already done in the previous session. So this angle will be minus 90 degrees, because minus 120 plus 30. And similarly this is 173, and this angle will be minus 240 plus 30 will be minus 210 degrees. So this you are aware of. So now we have line voltages. Let's draw the load. So if I go back, the load is in delta connection. Each load has a 2 plus j7. So impedance of 2 plus j7. So let me draw the delta load. So I just extend this and then connect it like this. And then one more load is there, and another load is here. So three loads are connected in delta fashion, and then I am just connecting it like this. So naturally I would label this as A, and I would label this node as B and this node as C for the loads. So we need to be a little bit careful in how we label it, so that we need to be consistent with that. So you follow one consistent way, and then you repeat it for all the studies that you are doing. So that is important. Now this is 2 plus, I think the value is 2 plus j7. So let me write that here. This is Z, Z and Z. So this is 2 plus j7. Now let's do the next task of marking the currents. So this current anyway is IA. This is the line current. This is current is IB. This is the line current, and this is the current IC. This is the line. I cannot directly calculate this. First I have to calculate the phase currents here. Then only then I can calculate the line currents. So what are the directions? So I think in my earlier video I had described about delta source. So anyway, so let's define a certain direction and let's be consistent with it. Now since this is A, I'll consider this current going like this as my A phase current. So I small a, I'll give it. So I capital A is the line current, I small a is the phase current going from here to here. So and what about this phase voltage? So VA is my phase voltage here. So I think we'll get confused with this VA. So let's call it VAP. I'm just searching for some kind of this one, or VAL. So L represents the load. So A phase voltage of the load. So you need to be consistent with this marking. So this is plus minus, and the current is I have given like this. Now to continue the same logic, so here the voltage that is coming between these two is here. So let me put VB here, and then the current IB, I'll just mention it like this. So I with small b, and then this is VBL, and this is VCL, and the current that is flowing will be something like this, I small c. Again, sorry for confusing you. I'll just put L here also, so that signifies load. Okay, so what is VAL? So you notice VAL is nothing but VAB. And what is VBL? VBL, this is plus side, this is minus side, nothing but VB. So you see this point is equal to this point, and this point is equal to this point. So VBL is nothing but VBC. Similarly, VCL is nothing but VCA. So this is plus and this is minus. VCL is nothing but VCA. So this exactly. So based on the way I defined in the circuit, so I can just equate it and then say VAL, VBL, and VCL. Again, don't confuse with the line voltage as L, but it's a load. So L means load. So this is load phase voltages. So one thing you notice, for a delta system, the line voltage is equal to the phase voltage, because they are just directly parallelly connected, that you can see immediately. So now once I know what is VAL, can I find IAL? So of course I can find IAL, just divide by Z. So because VAL is applied across A to B and Z is the only impedance, and then the only current that is flowing here is IAL. So I can find IAL. So not only IAL, I can find IBL, I can find ICL also. All these three currents. So how do I find them? Just VAL, VBL, and VCL all divided by the impedance. Then I get the currents here. So we'll do that calculation. So what are these? These are phase currents of the load. So let's use MATLAB interface and then we calculate that. Okay, so I have a clear screen. So let's define VA. VA is 100. VB is 100 exponent of I into minus 2 into pi by 3. So this is 100 e to the power of I into minus 120 degrees. So 2 pi by 3 is 120 degrees. So this will be my B phase voltage, and VC is exactly the same thing. Only thing difference is this is 4 pi. So my VABC, I can define it as a vector. First row is VA, second row is VB, and third row is VC. So let's just run this and check if everything is fine. Okay, on the right side, I am getting VABC. So this looks correct. So now, what are the line voltages? So how to get the line voltages? Just some time back you had seen that, let me refer to here. This one we have defined. So just multiply by root 3 into 30, I'll get the line voltages. So that's what we'll do. So why we should multiply root 3 into 30, I've already explained in the previous videos. It's basically just a vector addition. So VABC is nothing but, in fact I can show it here. So VAB is nothing but, from here I go minus VB plus VA. So that's what it comes to. And similarly VBC, VCA, you can do that. We have already done that. So this is a shortcut way of finding VABC. So let's do that here. So VABC line. So I'll just put underscore line. So these are line voltages. So VABC into square root of 3 into exponent I 30 degrees. So 30 I have to convert into radians, 180 by into 180 divided by pi. So this is the expression for getting the line voltages. So let's see if it's working correctly. So here on the right side you can see the line voltages. So the magnitude is all clear. So 173.2 I was telling. So that is confirmed. For the second one, minus 90 degrees, that's why it is minus I. Now what are my phase load currents? So IABC load. So VABC line is nothing but VABC phase. So this divided by the impedance. So since it's a matrix, it will divide by all. So what is my impedance? So 2 plus 7I is my impedance. So let me run this once again. So on the right side you can see the currents. So this is A phase current, this is B phase current, and this is C phase current. So let me display it. So IA load, IAL, I am calling it IBL. So IAL is nothing but IABC underscore load, the first element of it. Now I want to display both magnitude, so absolute value of that, and the angle of that. So how do I do it? In fact, I think the absolute value will be same for all. So let me just show you that. I'm just printing everything together. Angle of IABC. So this angle will be in radians. So I'm multiplying by 180 and dividing by pi. So it will show it in degrees. So let me run this. So here you see 23.792, 23.792, 23. This is exactly the same magnitude for all these three currents. So basically the above three currents are this. And the angle is minus 44, minus 164, and this I'll round it off to 76. So they are in turn separated by 180 degrees. Sorry, 120 degrees. So let me write it down. Let me record this answer. So I got these three currents, just now I calculated, divided by Z. So 23.792. So I'll just round it off to 23.8. And the angles, minus 44 degrees, minus 164 degrees, and 76 degrees plus. So the difference between these two is 120, difference between these two is also 120, and difference between these two is also 120. You can just verify that yourself. This is in amperes. So these are what? These are phase currents of the load. Now finally I want to find the line currents. So just go up and apply KCL. So at this node, if I apply KCL, then IA is the incoming current, and ICL is incoming current, and IL is the outgoing current. So incoming currents equal to sum of incoming currents equal to sum of outgoing current. So let me write it here. IA, or I can write IA equal to ICL minus IAL. So this is the first one. So what is IB? So IB is the incoming current, and the outgoing current is, I'm sorry, I think I made a mistake. Let me write it in this format. IA is the incoming current plus ICL is the incoming current minus IAL is the outgoing current. All of them should be equal to 0. So from this, if I'm interested in only IA, then IA will be IAL minus ICL. So this is what is this. On the same way, IB will be, so apply Kirchhoff's current law here. So this I capital B, I'm sorry, this is capital A, I'm sorry for the confusion. This is capital A and this is capital B. So I capital B is nothing but IB minus this one, IBL, so minus IAL. Similarly, I capital C is nothing but I, so this is I capital C, ICL minus IBL. So this is my KCLs for all that. So let me highlight this separately. This is KCL at ABC of load. So same thing I will enter into my MATLAB code, then I will be able to get that. So this is just for display purpose. So IAL equal to IABC of load first element, IBL and ICL. So I'm just getting the load currents, the second element of the matrix, and this is the third element. Now I have these three currents, then my line currents. So what is my I capital A? Is the KCL we have just written, IAL minus ICL. So IAL minus ICL. What is IB capital B? So this is IBL minus IAL. Finally IC. This is ICL minus IBL. So I have these three currents. So again, if IABC, if I define it as a matrix of line currents, I just combine these two, or combine these three currents, and combinedly I want to display their absolute value of IABC and angle of IABC. So this will be in radians, so multiply by 180 and divide by pi to get it in degrees. So this is what is the line currents. So here I'll say disp line currents. So just a message to display. Whereas what were these? These were load phase currents. So using simple KCL, we are able to calculate this. So let's run this code and see. So here is the output. So 23.79 to 23.7, these are all load phase currents. These are all line currents. So the magnitude is 41.2. So let me write that here. So therefore I capital A, I capital B, I capital C, these are line currents, and the magnitude is 41.2, 41.2 and 41.2. So balanced three-phase system, so all will have the same amperes. What about the angle? So this angle is minus 74 and this angle is 166 and this angle is 46. Okay. Now compare the angles of See, what is the angle of IAL? It is minus 44 and angle of IA is minus 74. So this confirms our earlier analysis. So in a delta, line current will be root 3 times the phase current, and line current lags phase current by 30 degrees. So you notice if I draw it as a vector diagram, so what is IA? Minus 74 degrees. So this is a 0 degrees. So this is IA 41.2, angle is minus 74 degrees. And if I want to show IAL, that is phase current, so 23.8. IAL is 23.8 degrees and this angle is minus 44 degrees. Therefore, this phase difference is 30 degrees. So the line current, so this is the line current and this is the phase current. So line current is lagging the phase current by 30 degrees, but its magnitude is increased by root 3 times. So that's what you can confirm it here. Now, some of you might say, what about phase B? So here the phase B is minus 64, but why it is here plus 166? How come it is not 30 degrees apart? But then if you examine a little bit closely, take minus 164 and subtract 30 from it. So I'll just do that here. Phase of B. So minus 164 minus 30. So that will be how much? So I'm just adding them. 194 with a minus sign. Now you know that its total is 360 degrees. So if I measure anti-clockwise, you will go like this, and if you measure clockwise, you will go like this. So 166, that is the computer is saying, is actually measured from clockwise. So the point is minus 194 is equal to 166. How? So I can just look at the magnitudes. If I add them, 4 plus 6 is 10 and this is 360 degrees. So it is exactly matching the same. So this I can actually write is equal to 41.2 angle minus 194 degrees. So because we use a computer, it displays the angle like this. And here it is again straightforward. 76 minus 30 is 46. So this is okay. In fact, everything is okay. So this is what is the analysis of star connected source and delta connected load. Just we'll do one final this thing. I want to know what is the complex power. So complex power is root 3 VLIL and active power is root 3 VLIL cos phi and reactive power is root 3 VLIL sin phi. This is based on what do you mean? In fact, this is nothing but S cos phi and this is nothing but S sin phi. So phi is the phase angle of the load. That is the power factor of the load, cos phi. Whatever. So this one is actually 3 into V phase into I phase also. You can just verify that here. So let's find S here. This is star delta connection. So root 3 into VL is 173 and IL, how much was IL? 41.2. So this is S equal to square root of 3 into 170. I know I should not do this. I should use the variables, but then it's okay. 41.2. I'm being a little bit lazy, that's all. So I get 1, 2, 3, 4, 5. Oh, this is an interesting number. 1, 2, 3, 4, 5 to the power of 0.4. So I think I'll come back to this and then examine it again. So 1, 2, 3, 4, 5 volt amperes. So this is the power. Now if I want to know active power, this is a complex power. So the phase is nothing but the angle of the impedance. So here you notice, I think it is it 74 degrees? So let me just use my prompt here, angle of 2 plus 7i into 180 by pi. Yeah, 74 degrees is the angle of the impedance. So 74 degrees. So I can just do Vi cos phi, so or S cos phi. So S into cos of angle of 2 plus 7i. Similarly, the same thing I'll repeat. So this I'll call it as three-phase power and three-phase reactive power. This is sine. So let's run. I think we are almost coming to the end of the thing. So active power is 3391.5. watts and reactive power is 1187 watts. So this is about PQ and S. So I think you understood something how to deal star and delta. So in the next video we'll take the opposite case where the source is delta and the load is in star. So let's see how it happens.